Alright, let's get into it. So my name is Andrew Stovell. I've been working with Dr. James Walsh at the University of South Australia in the wearables lab to program this robotic arm using Unity. And today we're going to be talking about the Unity solution that I've created, touch briefly on how ROS works and how ROS Sharp works and how you can program your own functionality for your own robot in Unity, which then opens you up for programming with AR, VR, or whatever else you'd like to do that Unity can already do. So the solution currently has two scenes. It's got the tabletop scene and the main menu scene. If we run the main menu scene, we can choose to either use the real arm, which is connected by USB to whichever intermediary device we're using. So in this case, it's connected to my computer. So the IP for the bridge, which we'll cover in a minute, the IP for the bridge is set to my computer's host IP. Whereas if you were connecting it to, say, a Go1EDU robot, which this arm is designed for, then you might set it to the robot's IP as you connect to it from wherever the app is running. So whether you're running the app on a tablet or a PC, however it is you connect to the robot's network, you would set it to that IP. And then otherwise you could use Gazebo to simulate a virtual model of the robot, and again that just uses the host IP at this stage. So I just wanted to quickly show off what it's like if you open the application using the simulated arm in Gazebo. And you can see the model here is a little bit shaky, which is a bug that needs to be worked out by someone else in the future. We've just been using the real arm so that the real arm doesn't have this issue. And in the spirit of transparency, you can see that shakiness causes some very odd behavior. Okay, so let's open it up with the real arm now and show off its intended behavior anyway, and show some of the user interface. So when we first start it, ROS starts and the planning scene starts. So the planning scene can be seen in RViz, which pops up, and you can see it there. And I just minimize all of this stuff for now. So this does take a little while to start, but once it gets going. Okay, so the first thing on the right, we have the jump to target buttons, which allow us to jump to the named targets that the robot has. So the arm, for example, has home, up, and sleep, which you can see in here. This is it moving to the up position and the sleep position. And then the gripper, the same thing. We have the open, middle, and closed positions. We can also control the gripper using like a finer control, using a slider. Currently we only use boxes. This could use cylinders or anything else. To place a box, you just have to right click and then you can follow the instructions in the bottom left of the screen on the UI there. You can then scale the box, rotate it, or position it wherever you need it to be. You can also stack boxes up on top of each other in order to build your planning scene. As you place boxes or move them around, the planning scene is updated with information to allow the planning scene to detect and avoid collisions. Finally, in the UI, you'll notice that we have the grasp cube and move to cube buttons. To grasp or move to a cube, simply select it as a target, which is when it turns blue with the orange dot, and press whichever button you'd like. The move to cube button will simply move the grippers to the cube, but it will not pick it up, whereas the grasp cube will pick it up. After grasping a cube, you'll be given a target cube to drag around to place where you would like to put the cube. When you're ready, press the place cube button to place it there. This functionality can be a little bit hit or miss, and we'll come into that in a second. Okay, so with the demo out of the way, let's talk about how it all works by first talking about ROS, or the Robotic Operating System, which is a set of software libraries and tools which help you build robotic applications. For the most part, we just need to know that it basically acts as a network of publishers and subscribers, or servers and clients. But for now, let's just focus on the publishers, the subscribers, the messages that they send between each other, and the topics that they're sent over. A ROS message can contain any data that you would like, whether it be the name of the robot, the state of its joints, or the position of its grippers. Our solution uses the ROS Sharp Unity plugin, which provides a library of publishers and subscribers, as well as methods to serialize messages to send them over a WebSocket, so that we can publish a message in ROS and receive it in Unity, or we can publish a message in Unity and subscribe to it in ROS. In our solution, we have a ROS node called the executor, which is defined in the executor.py file. Within this node is many subscribers and publishers, so that, for example, if we were to send through a grasp message from Unity over the Unity pick topic, our grasp subscriber could execute the moveIt commander's grasp function and pass in that grasp message to have the robot pick up a cube, for example. And continue on with the example, once the cube is picked up, we could then use the attach object publisher to publish a string back to Unity, which just says which object it is that we've attached to the grippers to update the Unity scene accordingly. Finally, in the Unity scene, when the user presses the place button, a pose stamped message is sent back to our place pose subscriber, which can then call the move commander's place function to place the cube. Ideally here, we would use a place location message, which, unlike the pose stamp message, also defines the approach and retreat trajectories of the arm so that you can get a fluid place and then retreat motion. So this is what causes our place function to currently be a bit dodgy. Unfortunately, this is due to a bug with ROS Sharp, where for some reason a place location message couldn't be published, even though there was nothing wrong with the message, but hopefully someone else can figure that out and improve our solution in the future. This is the last time that we will see this graphic, but I just wanted to point out that in ROS Sharp, all publishers just extend from the Unity Publisher class, which is in the ROS Sharp ROS Bridge client namespace, and all subscribers extend the Unity Subscriber class. So as long as ROS Sharp has an implementation of the message type that you would like to send, you can just extend the, for example, Unity Subscriber and specialize it with the message type. Then when writing your own custom publishers or subscribers, it's just a matter of making sure that the topic and the message are initialized, and then writing a function which will populate the message with the data that you want to send before finally calling either the publish or the subscribe function, which is contained within either the Unity Publisher or the Unity Subscriber class. I know a lot of this sounds like a mouthful, but the best thing to do is just get in there and do it. And I would suggest starting with simple messages such as string or float before moving on to more complex messages such as publishing a grasp or a place location message. Fortunately, ROS Sharp comes with a rich library of predefined common message types, and if you have your own custom message that you need a ROS Sharp equivalent message type of, they have a tool in the Unity GUI that you can use. Alright, I think we'll wrap it up there. Apologies if I lost you along the way. This video did get quite technical. While we didn't go in depth with how to install individual plugins or how to use every single tool, you can find all of that information in the repository. Currently, the repository is private and you need permission from someone in the wearables lab to access it. However, hopefully it'll be released publicly after it's been reviewed by someone who isn't a student, and then we can kind of get some open source collaboration on it. Thank you for watching, and if you have any questions, feel free to email me. This is my personal email here rather than my student email, as I'm finishing up university soon. I may be slow to respond, but I will try to respond with answers to your questions as soon as I can. Thank you again, and have an eye-opening rest of the week. Bye.